All right, good evening, class. Sorry that we're having to meet like this. Some unplanned company came from out of town. Is only gonna be here for tonight and tomorrow for the 4th, and then they're going back, and so um, kind of impacted our evening. Um, so, thanks for understanding, but um, I'll still do the lecture I would have in class. Obviously, it's going to be shorter because there's not going to be time for you all to work. So just like before, please record or pause the recording when we do practice problems so that you can practice them and then you can see how I do them. All right? So what we're going to be doing tonight is going through logarithmic functions, and then we're going to review the week 6 material. Okay? All right, so logarithmic functions, we're going to talk about evaluating a logarithmic function with base b, with base e, and using them to solve problems, okay? So logarithmic functions, you read it as f of x equals log base b of x. And so the b at the bottom, this b down here, that's the base, just like the bases for exponential functions. Okay, and so that's going to be something that is going to be tied to exponential functions, and the idea of a base that we talked about earlier is going to be super important when we start thinking about exponential functions and how logs and exponentials are related. Logs and exponentials are actually inverses of exponential functions. So I want you to notice something, that we have the base b here, also occurs there in the exponential function. The y here is the y there in the exponential function, and the x here is the x in the exponential function. So those all go together. So when we talk about base b of a log and base b of an exponential, they're the same number. So what that really means is that logarithms are exponents. That's really what they are. Logarithms are exponents, and that you need to have that kind of mindset behind it, because that's what really makes logarithms unique and makes logarithms something that we can actually use to be able to solve equations involving exponential functions, like we did last time in class. But now we're going to have a method that we can use to solve using logarithms. Okay? And so we're going to practice, like when we go to evaluate logarithms, you got to think about what exponent of the base gives the big number. Okay, so like for example, if I have log base 5 of 125, okay, so you're going to think about what exponent gives you that number. Well, what I like to do is I like to say, okay, I'm going to say that this equals something. I don't really know what the something is, but it equals something. Okay? And so then we're going to change it out of logarithmic form into exponential form, which means it's going to be 125, the big number, is going to be equal to 5 to the x. Now you could flip-flop those sides. It doesn't really matter. So now you got to think about, okay, 125, what is that? 5 to what power? Or 5 to the first is 1, 5 to the second is 25, 5 to the third, that's 125. That means that x is 3. Okay? And we could do it the way we did yesterday when we were using, or last class when we were using exponential functions, is you could say, hey, I'm going to make 5 to the third equal 5 to the x. Right? Same thing, you get that x is equal to 3. Okay? So practice this one. What would the log base 2 of 1/64 be? Pause the video so you can practice. Okay, so now I'm going to do it. And so log base 2 of 164, we're going to say that equals x, which means that 1 over 64 equals 2 to the x. And so we got to think about 2 to what power? Well, it's 1/64, so we know it's got to be a negative. Okay, and so 2 to what power gives me 64? Well, 2 times 2 is 4. times 2 is 8, that's third, times 2 is 16, times 2 is 32, times 2 is 64. So that's going to be 6, the 6th power, but because it's in the denominator, it's got to be a negative. So that means that it's going to be negative 6 is what x equals. Okay? So, same idea. You could also have written this as 2 to the negative 6 equals 2 to the x, which then you're going to get negative 6 out of it. Okay? Hopefully you got that. Hopefully that makes sense. Okay? You can also evaluate log functions using a calculator in some cases. So the one that you can do in the calculator is log base 10. And so if you look at your graphing calculator, the log base 10 button is not on your calculator, but what you do see is just log, L-O-G. That log on your calculator is the log base 10 log. Okay? You also see, if you hit right below that, an ln. And that's the natural log. That's the log with base E. And we just shorten that to ln. Okay? And so those are two logs that are shown on your calculator that we can use to calculate values with. Those are the only two that we can do from the calculator. Any other bases we can't do in the calculator straight away. I mean, there are ways you can get there. If you go into, I believe, the math button, yeah, and you can do it with different bases. But there's other ways you can do it as well. Okay? So we're going to practice. So I want you to use your calculator to evaluate log of 300. Okay, so I'm going to give you time. So pause your video here if you want to practice this. Okay, so we're going to go in our calculator, we're going to put log of 300. And when we do that, I get 2.477 rounded. Okay? So your calculator, that'll give you very quickly the answer to any log question you might have. All right, hopefully you got that as well. So there are some certain properties of logs that hold true. One of them is that if you have the log base b of any log of any base, if 1 is the number on the inside, that has to equal 0, right? Because if we think about transforming this, this is going to be that 1 equals b to the 0. And we know that anything raised to the 0 power is 1. And so that's that if the inside number of the log is 1, the outside number, the one that it has to equal, is 0. If you have log base b of b, so if the inside number and the base are the same, then the result's going to be 1. Okay, and that's because we'd have b equals b to the first, right? Same thing. Okay. The log base b of b to the x is equal to x. And so what you can really think in that situation is that these two b's cancel, and you have, that's where you get the x's left over. That's kind of how I think through that. Last one is that if you have log base b of x equals log base b of y, then x equals y. If the two log bases are the same, much like exponentials, right? If the two log bases are the same, then that means the insides are the same. Okay, so you can just kind of get rid of those logs and just set the insides equal to each other. All right, so let's try a couple here, right? So let's think about what would be log base 501. Well, that's the first property. Log base 501 would be 0. Okay, let's try the next one. Log base e of e. Pause if you want to practice. Okay, this one, since the insides are the same, this is the second property, this would be equal to 1. Okay. Last one, 8 to the log base 8 of 30. Okay, you have to think about this one. So pause it here if you want to try it yourself, and then we'll try it. All right, so this is one of those situations where logs and exponentials are inverses of each other. Notice that the log here is in the exponent. Whoops. The log here is in the exponent, right? And so when it's in the exponent and the base are the same, so we have 8 and 8. Those are the same bases. When we have those set situation, what we can do is we can say, okay, just cancel these two out, and this is left with 30. That would be our final answer for that problem. Hopefully you got that. You probably may not have got the last one because we didn't really cover it, but I want to make sure we showed that as well. All right. Now the next thing we can do is we could solve logarithmic equations. Okay, and so like this one, pause before I solve it so you can try it yourself. Give you a second to pause it. Okay, so now I want you to notice the log and the log, exact same log, right? So since those are the exact same log, we can just set the insides equal to each other. Okay? And so since the insides are equal to each other, we just solve this. So we subtract 4 from both sides, and we get x squared equals 25. And then that means we square root. And so that means that x is equal to plus or minus 5. Right? When you square root, you have to consider there could be both solutions there. Hopefully you got that as well. All right, so that's the end of logarithms. Obviously, we're not taking a break. So we're going to move right into the review questions that we have for this week. Okay? And I've kind of reduced some of the problems that are on there, so I only show a few of them, just so I had more space to write on here. The PowerPoint will have more problems that you could practice that are similar if you wanted to practice those from the book. But I reduced some of the screen on here so I would have more space to write. All right, so question 2, population of a herd of deer is represented by that function where t is given in years. To the nearest whole number, what will the herd population be after 6 years? So pause here so you can try it, and then I'll try it. All right, so it says after 6 years, so that means it's going to be a of 6, right? Because the t is going to be 6. That's going to be 205, 1.13 to the 6th. And so we take our calculator, we put that in. And when I do this, I get 426.8. But it said to the nearest whole number. And so we would say that this is 427 would be the herd number, 427. Hopefully you got that for your answer. Next question. It says determine whether table 1 can represent a function as linear, exponential, or neither. If it appears to be exponential, find a function that passes through the points. Okay, give you a minute to look at that, and then we'll move forward. Hopefully you pause that and work through it. So we look at this one, right? And so we're going to say, okay, is this linear? First thing. So x is going up by 1, right? So that's good. That's that helps us for a constant x value kind of thing. But if you look, the y is not staying consistent, right? We went down 2.1, and then we went down, 0.73, 0.63. So not consistent. So not linear for sure. Definitely not linear. Not going to be linear. So maybe it's exponential. Well, if we kind of look, these numbers are very similar, right? This is 3, and we got 0.9, 0.27, 0.081. Well, that's almost like 9, 27, and 81, which are all multiples of 3, right? So it really kind of looks like it could be exponential, okay? But it's exponential going downwards. It's decreasing, so it's got to be exponential decay of some kind. It's definitely decreasing. And so we're going to use the equation that y equals a times b to the x, right? And so, like we did in class, we need to pick 2 points. And so we're going to say that 3 is equal to a times b to the first, and 0.9 is equal to a times b to the second. Let's take that first one and solve it for a. So that means that 3 over b is equal to a, which means that this equation is going to be 0.9 equals 3 over b times b squared, which then the b and the square would cancel, and so you'd have 0.9 equals b, which means that b is equal to 0.3. Okay? And so now we have that. Let's take that result, put it in place here, and so we'd get that 3 over 0.3 is equal to a, which means you take 3 divided by 0.3, and we get 10. 10 equals a, right? So that means our equation is going to be 10 times 0.3 to the x. That's what you should have got from that. Definitely exponential. All right, number 6. Husmay wants to save $5,000 for a down payment on a car. To the nearest dollar, how much will she need to invest in an account now with 7.5% APR compounded daily in order to reach your goal in 3 years? Okay, so pause it if you want to practice it, and then we're going to work through it. And this slide had several problems on it. We're going to do a couple. I'm just going to put 6 on this one. We're also going to do 8 on this one. Okay, so we're going to use the equation that A equals P1 plus R over N to the NT. So she needs... This one's an interesting one because she wants to save 5,000. So that's what we want at the end. We need to know what she needs to put in for P. So we don't know P yet, but we know that 1 plus our interest rate, which is 7.5%, so 0.075, divided by N, which is going to be number of compoundings is daily, so that's 365 compoundings times 365, and T in years is going to be 3. Right? That's what was end up happening up there. So this is a little bit of a different one because we have to get that number next to P first before we can do anything else. So let's put a calculator. 1 plus 0.075 divided by 365 to the 365 times 3. Okay, so this number I get is 5,000 equals P times 1.2523. That's rounded. Now if we take 5,000 and divide it by the answer we got, I get that her initial investment needs to be $3,992.67 if she wants to reach her goal in 3 years. Okay, hopefully you got that as well. All right, number 8 on that same slide with 6 says suppose an investment account is opened with initial deposit of $10,500, earning 6.25% interest compounded continuously. How much will be in the account be worth after 25 years? So pause it so you can practice it. Okay, so remember this equation is A equals PE to the RT, right? And so we're looking for the amount at the end. This P is 10,500. E to the interest rate, which is going to be 0.0625, and T is 25 years. So we're going to take our calculator, and E to the 0.0625 times 25. I need to put that in parentheses. I get, at the end of 25 years, that we got $50,092.70 in that account. Hopefully you got that as well. Okay? On to question. Oh, I think I deleted a slide. Oh, sorry. On to question 11. So question 11 says the graph of f of x is 6.5 to the x is reflected about the y-axis and stretched vertically by a factor of 7. What is the equation of the new function? Say its y-intercept, domain, and range. Oh, I know why. I got rid of 9 and 10 because they did very similar things that we're going to do now. So you can practice 9 and 10 on the previous slide. 11 is going to do very similar stuff. So it says, first thing, it says it's reflected about the y-axis. And so that's what's impacting x. And so right away, we can take our function, and we know it's going to be 6.5 to the negative x. Right? Because the x is going to be changed. The x is going to be modified. The x is going to be flipped over the y-axis. And so that's impacting the x. That's going to make that change. It's stretched vertically by a factor of 7. So that's impacting the y value. It's making the y 7 times bigger. So that's going to be 7 now times this. So the 7 should go out inside. Okay? And so now when we do this, now we say, okay, what's the y-intercept? Well, the y-intercept is where x is equal to 0. So if you put a 0 in for the x, you're going to get 7 times 6.5 to the 0. Well, that's just going to be 1. So the y-intercept then is at 0, comma 7, because 6.5, this would be 7 times 1, which would just be 7. So there's your y-intercept. The domain is, again, like domain for all exponential functions is all real numbers. So domain is all reals. That's going to be negative infinity to infinity. The range, now we got to think about this. It's going to cross from 0, 7. There's no shift vertically, so we know it's going to have the y-axis or x-axis as its horizontal asymptote. Okay, but because of the negative x in the exponent, this is going to be exponential decay, right? And so it's going to go start real high, go through 7 on the y-axis, and go down to the x-axis. And so this one's going to be, the range is going to be from 0 to infinity. Hopefully you got that for your problem. All right, number 12. The graph shows transformations of the graphs of y equals 2 to the x. What is the equation for the transformation? So pause it here so you can try. Okay, so 2 to the x, exponential growth, so it's still showing growth, so that's okay, right? It should go through the y-intercept should be at 1, right? Because if we make x be 0, y would be 1. But now the y-intercept is actually like negative 0.5, 1.5, negative 1.5. So it's definitely been shifted down, right? It looks like it's been shifted down 2, actually. It's been shifted down 2 because the new horizontal asymptote is right here, okay? And so we know it's going to have at least this. It's going to be f of x equals 2 to the x minus 2 at least. At least that much. Let's see, what else could that be? Because I don't know if that's going to be enough to make it have that shift. Because would that give us, if we make our x be 0, that's going to be 1 minus negative 2. That would not give us the right y-intercept. right? Yeah, that's not going to work. Because we know it's going to be shifted down 2. It appears that way anyway. But it's probably going to be shifted over as well. Because it's got... The issue is this y-intercept here is not what's going to show up in our function that we have written up there. Because when we make x be 0, we're not going to get negative 1.5 out of that. We're going to get negative 1 out of that. Okay? And so what we need to do is it's probably been shifted right some. As well as shifted down. It might have been shifted right 1. I'm not really 100% sure, but one thing we could do, oops, 1 second. I'm trying something on my calculator real quick, if you're wondering why the pause here. Yeah, so it looks like, because like this point right here really should be right here. So it's been shifted down 2 and over 1. So I think the equation needs to have a minus 1 here to be able to get the right number. Because now if we put 0 in for x, we're going to get 2 to the negative 1, which is 1/2, minus 2, which is negative 1/2. So that's correct. So this is the right equation. Now let's say if you can't see that, let's say you don't recognize a shift. Well, what else could you do? Well, we could take this point that we know, and that's going to be, let's make like a little table here, right? XY table. You would say that x is 0, y is negative 1.5. And then we also know that at 2, y is 0. Okay, you can take that table and you can put it into Desmos and have it create the equation for you. So I'm going to do that on my computer. I'm not going to be able to show that on my iPad because I don't have Desmos on my iPad. But if we put those points in, 2, negative 1.5, and then put in 2 and 0, right? Just like I showed you in class. And then you're going to go to the regression and do a exponential regression. What in the Sam hell is it doing here? Oh, that's a weird function. I don't know about you, but mine turned out to be a really weird function. Two, 0, 0, negative 1.5. I don't think Desmos worked in that situation. I get a really weird number at the end. Oh, it's because it's not using the right form. That's why. It's not going to do our shift and everything that we want to do. So never mind. Don't use Desmos with that. So what I did when I did that is I looked at the horizontal asymptote. That gave us the negative 2 shift downwards, right? Okay. And so our 2 to the x should go to 1. It should go through, like it should be coming like this. Through 1. But that y-intercept got shifted down. We know it got shifted down 2. Right? For sure. And so it should be at 1. It should be right there. But it's not. It's at negative 1.5. So that means it also got shifted over. And so we're going to take this and where that lines up with the graph right there, that's going to show our horizontal shift. And so that's why we got the 2x minus 1 minus 2. Okay? We use the point that it should be at, using the idea that the horizontal asymptote that's in here is going to create our vertical shift downwards, and knowing that our y-intercept should be moved down 2, but it didn't. It got moved down more than 2, or it didn't get moved down 2, but we can use the point that it should be at, which was at negative 1, line that up with the function, and that's going to tell us our horizontal shift. Okay? Hopefully that makes sense. All right, number 17. So we're doing this one. Notice I skipped a lot of questions on 13 through 16 because we practiced that in the beginning, and 17 and the rest are more important than this one anyway. Okay? So if we want to say, let's solve for x for this function, okay, by converting it to exponential form. So we're going to say, okay, we're going to have log base 64 of x equals 1/3. That means it's going to be x is equal to 64 to the 1/3. So we can literally take our calculator and put that in. And when we do that, we get x equals 4. Okay, super simple, straightforward question. All right, last two. I'm going to do 18 and I'm going to do 20. So 18, pause here so you can practice. Okay, so 18. We're going to evaluate that without a calculator. Whoops. So we're going to say, okay, log base 5 of 125 equals something. We don't know what that something is. So we say 1 over 125 equals 5 to the x. Well, what's that going to be? We know it's going to be a negative. And 125 and 5, that's 3. So that means that negative 3 is what x is. Okay? And 20, find the log of 4.005. Literally putting that in our calculator. Log of 4.005. And I get, round to the nearest thousandth, which is the 3 decimal places, 0.603. That's my final answer. Hopefully you got the same. All right, so that's it. If you have any questions, please reach out to me via email. I'll be in touch. You do need to send me a text message or an email just for attendance purposes that you checked in. Hopefully you all watched the video. If you didn't, that's fine. I mean, you can see the notes that are in there. But we will continue Chapter 4 next week, so this is not all we're going to see in Chapter 4. We will continue that next week to have you ready for your Chapter 4 quiz next week. As a reminder, tonight you have your discussion question, initial post due. Sunday you have your replies due. Sunday you also have sections 3.1 or 3.11. The first 3 sections in Chapter 4, and your Chapter 3 quiz and review. So busy weekend. Hopefully you feel like this time was valuable, that you can use this time to stay ahead on the material. Hope everybody has a safe 4th of July tomorrow and enjoys time with friends and family. All right. Until then, I will see you on Tuesday.